Let's kick off this explainer with a little secret. Machine learning, it might look like pure magic from the outside, but under the hood, well, it's really just plumbing. Seriously. Whether you're running a massive billion parameter language model in a sprawling data center or just a real-time vision model right there on your smartphone, the data is flowing through a surprisingly similar set of pipes. So today, we're going to unpack exactly what happens between a model just sitting dormant on a disk and the silicon actually spitting out a prediction. Now, despite facing radically different hardware constraints, both of these environments actually trigger the exact same 9-stage pipeline. In a cloud environment, you've got a CPU that's so fast it can literally starve the GPU, but they're separated by a massive PCIe or NVLink bottleneck. Then on mobile, you've got a system on chip where the CPU, GPU, and NPU are all sharing the exact same physical memory, but they're constantly fighting over asymmetric capabilities. So yeah, completely different bottlenecks for sure, but they have the exact same 9 problems to solve. To demystify all of this, we're going to follow the chronological lifecycle of a model file structured into 4 clear phases. Stages 1 through 3 cover prep, 4 and 5 handle logistics, 6 through 8 are execution, and then stage 9 wraps up with our final takeaways. Let's jump right into stages 1 through 3. Prep. This is all about getting the model weights off the desk and figuring out what math we actually need to do before we ever touch an accelerator. These are the first 3 hurdles every single inference engine has to clear. Number 1, load and deserialize. 2, graph capture. And 3, IR lowering and partitioning. This is the crucial phase that takes us from a static file on a disk to a fully captured, actionable computation graph. Here's where things immediately start to diverge. For stage 1, the cloud environment pays a pretty heavy transfer tax. Weights usually bounce from the disk into host memory and then travel over a CUDA memcopy right to the device. Mobile, on the other hand, aggressively avoids copying data entirely. By using formats like flat buffers, mobile apps can read static weight shapes directly from the file system. It's essentially a zero-copy read, which is absolutely crucial for keeping that cold start latency incredibly low. Moving to stage 2, cloud frameworks have to actually decide whether to trace a graph at all. PyTorch's default eager mode just executes one operation at a time, driven right by the Python interpreter. But on-device runtimes, they simply do not have that luxury. They demand a pre-captured directed acyclic graph, or DAG. They absolutely need this static shape to plan everything perfectly in advance. And honestly, this is exactly why mobile frameworks push so hard for static shapes wherever they possibly can. So whether we're talking about torch inductor fusion, TensorFlow's grappler, or executorch partitioning, every framework uses stage 3 to optimize the graph for the specific hardware it's about to hit. By collapsing operations together, like taking a convolution, a batch norm, and a ReLU and just folding them into one single kernel, these frameworks stop intermediate tensors from constantly round-tripping to memory. It is all about avoiding those massive memory bandwidth bottlenecks. All right, moving right along to stages 4 and 5, logistics. The runtime has the graph, and now it has to decide exactly how to execute it and where to physically store all that intermediate data. This phase includes kernel selection and compilation, followed by memory allocation and planning. Basically, this is where our nice theoretical graph meets the harsh, unforgiving reality of hardware kernels and memory buffers. Notice how cloud systems often use just-in-time compilation, auto-tuning kernels against live hardware on the fly. They lean heavily on hand-tuned closed-source libraries like QDNN, or they emit auto-tuned Triton code. But mobile edge devices rely almost entirely on ahead-of-time compilation. They translate the graph into pre-compiled hardware executables that get cached directly to the phone's disk. You pay that heavy compilation cost exactly once, meaning the second time you launch the app, it is lightning fast. Memory is where the contrast gets even starker, actually. Because the cloud handles totally unpredictable tensor lifetimes, it requires these super complex dynamic caching allocators to grab massive chunks of memory upfront. Mobile is a completely different beast. It statically plans its memory offsets on a build machine, long before the code ever even hits a phone. It hard-codes exactly which buffers can be reused, sidestepping runtime allocators almost entirely. Okay, we've prepped, we've planned, we've allocated. Now it is time for the climax. Stages 6 through 8, execution. This is exactly where most of your latency bugs actually happen in the wild. These 3 stages cover placement and dispatch, kernel launch, and synchronization. Basically, this is all about enqueuing the work onto the chip, launching it, and this is the most important part, making sure the host CPU doesn't get in the way and ruin your performance.
To really understand why an inference pipeline stalls out, we absolutely have to define asynchronous execution. The CPU and the GPU, they are running on two completely separate timelines. The CPU's job is simply to tell the GPU what to do, and then it immediately moves on without waiting around to see the result.
I actually love this analogy from the source material. Think of the CPU as a kernel launching machine gun. It just sprays commands onto a CUDA stream, queuing up dozens of kernels before the GPU has even finished executing the very first one. This completely decoupled architecture is amazing for raw speed, right up until something forces that machine gun to stop firing and wait. But eventually, different chips do need to talk to each other and pass a buffer, say handing off from a GPU to an NPU. The cloud relies on CUDA events and stream synchronization for this. Mobile, however, hands off buffers using something called a DMA fence. This fence allows the consumer, like the NPU, to wait at the driver level using hardware semaphores. It's essentially passing the baton perfectly without waking up the CPU entirely. And that brings us to the silent killer. If you've ever wondered why your real-time app stutters, it's almost always right here in Stage 8. It's usually a stray line of Python code, like a seemingly innocent .item call or a print statement that accidentally forces the CPU to stop and wait for the GPU to finish its calculation. I mean, getting a value back to Python requires the GPU to actually be totally done. On mobile, the equivalent is a badly placed blocking delegate handoff, which can easily result in 3 CPU stalls per frame. It silently serializes what is supposed to be an asynchronous pipeline, and it is a massive performance killer. Finally, we reach stage 9, where we grab our results and zoom out to see the big picture takeaways. Retrieving the final result is a critical fork in the road. You can do a very costly copy back to host memory, like a CUDA memcp device to host in the cloud, or dequantizing to the CPU on mobile. Or, if you're smart about it, you can keep it zero copy. In the cloud, this might mean leaving token sampling resident on the GPU for the next loop. On mobile, it means using an A hardware buffer to instantly feed the next process, like a video compositor. The path you choose here is a massive latency lever, regardless of which hardware you're on. When we zoom out, the big picture becomes incredibly clear. Whether it's TensorFlow collapsing nodes or TensorRT fusing layers, everyone is fighting the exact same fight against launch overhead. The choice between ahead-of-time and just-in-time compilation, that's really just a slider you adjust based on your hardware constraints. And if you understand why a blocking delegate absolutely kills mobile latency, well, you already understand why a stray.item call kills cloud latency. It's literally the exact same bug, just wearing a different API. No matter what stack you prefer, whether it's PyTorch, CoreML, or Onyx, it really is all the same plumbing. They might use completely different masks, class names, and jargon, but they're all bound by this identical 9-step reality. They all prep the graph, manage memory logistics, and execute asynchronously. So, next time your inference pipeline stalls, I want you to ask yourself, which of the 9 stages is really to blame here? When your real-time performance dips, don't just immediately blame the silicon. Take a look at the plumbing. Ask yourself, did we fail to zero copy in stage 1? Did we completely mess up the memory allocation in stage 5? Or did we accidentally serialize our machine gun in stage 8? Because once you see these 9 stages, you really can't unsee them. Thanks for joining me on this explainer, and happy debugging.